Up to now, we've been looking at the behavior of matter as long as there is constant pressure, looking at how the temperature changes or the phases of matter change. Now let's take a look at what happens when we change both temperature and pressure. Up until today, when we've been talking about phase changes, what I mean by phase changes are changing from one physical state of matter to another physical state, like melting ice into water, liquid water rather. So you're changing from a solid state to a liquid state, or boiling water, you go from a liquid state to a gaseous state. That assumes constant pressure. Everything we've done so far, up to this point in this unit, assumes constant pressure. Okay? And what I mean by constant pressure is, this is stuff you could do in this lab room or at home or outside, and pretty much the air pressure is 1 atmosphere, close to it. It's actually on the average slightly less than that here, but you know, at 1 atmosphere is the average air pressure at sea level around the globe. What we're going to be looking at now is, well, what happens if you change the pressure? What if you go to Denver, Colorado, which is much higher up and your air pressure is a lot lower? What if you go in a weather balloon up to the highest reaches of the stratosphere or something, okay? What happens then, all right? Or if you just have a way of evacuating the air from a container, what happens then? That's what we're looking at. So we're looking at a comparison of physical states when we're changing temperature and pressure, okay? Changing temperature and pressure. All right, the first thing I want to look at is a generalized phase diagram for, it's kind of like an average of the behavior of almost all substances on our planet, okay? Not every substance, but almost all, okay? So this is a typical phase diagram. That should be I right there, typical. Okay, a typical substance, all right? Now, that doesn't mean that if you have a specific substance and you run tests on it, that it's going to have this exact behavior. The shape of the lines or the angles and the curves might be just a little bit different, but in general, it'll look very similar. You'll look at it and you say, oh, that looks very similar to this one, okay? Mm-hmm. So, we're going to be looking at temperature down here. We're going to be looking at pressure on the vertical axis. Now, the temperature could be almost any temperature. It would depend on the substance as to what the temperature ranges would be. Okay? You have to draw that line all the time? You could just draw a little simple arrow. You don't have to make it more as all-encompassing as me. I'm just trying to make sure we're clear. Okay? All right. And since we're looking at phases, I have regions within this graph. Regions within this graph for solid, liquid, and gas behavior. Okay? So I'm going to put solids in this region over here. I'm going to put gas in this region down here. And liquids are going to be in this region here. Okay? All right. As the temperature increases and as the pressure increases, so if we were at 0 temperature and 0 pressure, we would start right here. Okay? Virtually down to almost nothing here. Okay? And as we increase the temperature and pressure, we look at that behavior. What we see is that there's a straight line with a positive slope initially separating solid and gases. Notice there's no liquids here. It's only going from solid to gas. If the pressure is low enough, almost every substance has no liquid. You have to have the substance under pressure for it to be in the liquid state. Okay? So in space where there's almost no pressure, there's almost no liquid anywhere. Okay? Water, throw some water out the door of the space shuttle. It's either going to be ice or it's going to be steam. But it won't be liquid. Okay? It will be for just a tiny fraction of a second, and it's gone. It'll be ice crystals or it'll be steam. All right? Now, it can be steam at negative 75 degrees C. But that's because the pressure is so low. So if you can have, as long as the pressure is low enough, I can have steam at a very low temperature. Okay? Yes.
You know how when it's cold and you breathe, like smoke comes out?
Yes.
Why is it liquid?
You get, you're talking about when it's cold and you see your breath, basically?
Yeah,
All right. What that is, in your body,
Oh my God.
your body has a lot of water, and it has a higher temperature than the ambient temperature around it. So there's a lot of vapor in your throat, in your lungs. Okay. In fact, if you didn't have a lot of vapor in your lungs would dry out and you'd die. Okay. So when you breathe out, in that air you're breathing out, there's a lot of water vapor. Now, when I say water vapor, that doesn't mean that's liquid water. It's little molecules of water that are small little pieces. You can't really see them. All right. So when you breathe out and the air is cold, those molecules of water slow down. They touch each other and stick and make little droplets. And when they get big enough, you start to see them, and that's what that looks like. It's the same stuff as in fog and in a cloud. Okay, except a cloud is a lot of times actual ice crystals and not water droplets. Okay, but fog is exactly like that. All right. Now, there's a point where we get enough pressure then, if we're continuing to move up in temperature and up in pressure, there's a point where the pressure gets great enough that we can start having a liquid. And the phase, and these lines are called phase. Oh, but let me ask you this. Just to reiterate a thing that we've learned in Unit 1, if I have a straight line behavior with a positive slope like this, how do you describe that graph behavior? What do you call that? What?
Positive correlation.
Well, it might be, yes, it's a positive correlation, or could be, but there's a name we have for that I asked you to learn in Unit 1. Wow, that's not good. That was 1 unit ago. I told you this class is very cumulative, right? What we learn in this unit, you got to know in the next. Avogadro.
What are you asking us?
What is the behavior between two variables? The result is you have a straight line with a positive slope. What is that relationship called? Oh my gosh. I guess I need to put that on Unit 10, on the Unit 10 test. It's called the direct relationship. All right. A lot of things in chemistry, you tend to make them harder than they have to be. It's like this ice cream calculations. If you just do one thing and then the next thing and the next thing, you can figure it out a lot of times without, it just seems confusing because it looks like a lot in the beginning. But you just do this, and then you do this, and then you figure it out. One foot in front of the other. Okay? How do you begin a journey?
You gotta start somewhere.
Yeah, with the first step. The answer to that question is with the first step. Okay? All right. Something else about this graph before we go much further. In the lab, when we do graphs in the lab, you are always dealing with an independent variable and a dependent variable. We are always in the lab moving around some variable. We're manipulating some variable, and it's causing a change in the other variable. Okay? The independent variable down here on the x-axis causes a change in the dependent variable, and you have to write your titles that way. Okay? In this case, this is not an independent variable that causes a change in the dependent variable. This is just comparing two different variables. Okay? So this doesn't require a title in the form the effect of independent variable on the dependent variable. Okay? This is one of those cases, and the graphs we did yesterday are the same way. They don't require that kind of title. Okay? All right. So now, between the solid and liquid phase, we also have a straight line with a positive slope. It's just a different slope. Okay? So as you increase pressure and temperature, you get to a point where you can start to have a liquid. Okay? But notice you don't get very far down the x-axis before you can't have a solid anymore. And that makes sense if you think about it, right? Things melt when you heat them up, right? But you can affect along this region here, this little narrow slice of the x-axis, you can affect whether something is a solid or liquid by changing the pressure. Okay? Now, the boundary between liquid and gas is a little bit different. It's never a negative slope. So positive slopes are always going in that direction. Okay? Either here or here, but always somewhere in this region here, going in that direction. So this line, this curve here is never going downhill. It's always going uphill. But it makes a curve that looks something like this. Okay? So the boundary between liquid and gas, as you change the temperature and as you change pressure, you get a boundary right along here where below this pressure, above this temperature, you got a gas. And above that pressure and temperature line, you get a liquid. Now, if you remember, we talked about, in fact, the quiz we did, where we were looking at the graph that shows heat energy and its effect on temperature for water. That graph assumed constant pressure. There was no change in pressure on that graph we did with that quiz. Okay? Here, we're changing the pressure. Okay? And if you get the pressure and temperature just right for almost any substance, you can get a point right here that's pretty special. Now, when we were doing that other graph where the pressure was constant, let me remind you of that, show you that right quick, to show you, make sure you know what I'm talking about here when I'm referring back to it, because apparently we seem to be having some trouble remembering things. There it is. This graph right here. Okay? When you are in this region right here, notice the temperature's not going up. So yeah, so as long when you get ice up to the right temperature, that's a point at which you have both liquid water and ice at the same time in the same place. And when you boil water on the stove, you can see liquid water and gas at the same time. Make sense? But they're at the same temperature. All right? Well, if you get the pressure right, you can not only have liquid and solid at the same time at the same pressure, same time, same temperature. You can not only have liquid and gas at the same time, same temperature. You can have all three at the same time, same temperature. Liquid, gas, and solid, all in the same place, all at the same temperature. Okay? And that's pretty special, so we give it a special name. It's called a triple point. If we're talking about it, if it's in the notes, if it's part of the homework, it could be on the test. All right. Now, as we increase the temperature, okay, we're going to increase the temperature going in this direction. There is a certain point on the temperature. The temperature's on the x-axis, so this whole section along here, okay, there's a point at which the temperature becomes so high that no matter how much pressure we put it under, the substance no longer is actually a liquid anymore. Okay? So when we get to that point where we're having the pressure, the temperature high enough, and it's so high that no matter what amount of pressure you put it under, you no longer are able to make it into any kind of a true liquid. Something that new happens here. Okay?
What is that? What does it represent?
This is called critical temperature. And above that temperature, and it's different for every substance, but above that temperature, the substance can no longer be a liquid, no matter how much pressure you put it under. So it's like this line goes, this curve goes to here, just kind of disappears. All right? And this point here, this is called a critical point. Critical point is the intersection of the liquid-gas phase boundary, and all these black lines I have in this graph are called phase boundaries. It's the point on the liquid-gas phase boundary beyond which, no matter how much pressure you put it under, the temperature is too high to ever actually have a liquid. Okay? And so when you get into this range, the temperature is so high you can't have it actually be any kind of a liquid, then what you have is called a critical fluid. Or supercritical fluid.
Line in the middle right there.
Well, anywhere in this range. When you get up in here, you have a supercritical fluid. All right? Now, I want to be as clear as I can. Fluids mean it's something that can flow. Fluids means it's something that can flow. Okay? Both liquids and gases can flow. All right? So this is a region where we have something a little bit different from a liquid, a little bit different from a gas, and it's called a supercritical fluid. All right? Technically, given the right conditions, solids can flow. All right? It happens in earthquakes and such. All right?
What? Oh, I get it.
In earthquakes and such, you get solids actually flowing like liquids. Not just sliding over each other, they flow. That's a subject for earth science or something, not for chemistry right now, but it does that. Okay? All right. So that you can get solids given the right conditions that behave like liquids, basically. All right? Okay. Do you understand what we're talking about here, about what's happening?
Yeah, I mean, it's just a graph a little bit. But I get
It's
it.
just a graph.
I mean, a diagram, but I get it.
It's just a diagram.
I get
A
it.
diagram tells you a huge amount of information in a very small amount of space. Okay?
I get it. That's like, temperature wise,
All right.
Can we draw another graph?
We're doing another phase diagram.
Alrighty.
All right. This phase diagram is for a very common substance on our planet that behaves a little differently than almost all other substances.
Let me guess what it is.
Guess.
Repeat the question.
A substance that has a different phase behavior than almost any other substance on the planet.
Water. Oil.
You're right.
What is it?
Water.
Oh, me? He got me right there. What was that? What is that? Is that line supposed to be cooking like that?
Yes.
No. Say something. I was wondering.
This is water. It's almost everything else.
Whoa.
Water. Almost everything else. Do you see the difference?
Yeah, a little bit. Oh.
Thought it was the same.
Oh, that's cool.
Oh, okay, so it's not, so.
Do it again.
What's
Oh,
happening?
liquid goes like that.
Oh, it goes, oh.
Water's behavior, this solid to liquid boundary leans sort of back. It's a negative slope instead of a positive slope. Okay?
It was positive. It was going positive.
It was going positive. This is most substances are positive right here. Okay, that line right there. But water's slope is negative.
Where's the other slope?
I'm gonna draw that again.
What do you mean other
Where
slope?
it's like curving like that?
That's the liquid gas boundary.
Okay.
Okay? Now that doesn't mean the temperature is exactly the same and all that. That's not what we're talking about here. We're just saying that water has a different phase behavior between solid and liquid as you increase the pressure. Okay? Now I have technically leaned this line right here back too far because the way it leans back is so slight that it's hard to see unless I just sort of overemphasize it a bit. Okay? Just for the record and to be fair, okay? But this behavior is really important, okay? Without this behavior, fish couldn't live in frozen lakes in the wintertime. Without this behavior, your ice cubes wouldn't float on top of your tea.
Wow.
With this behavior, we get potholes. With this behavior, we get rock slides. A lot of things that happen on our planet, it has to do with this behavior right here, okay? And this is due to a special property of water. It's called hydrogen bonding. So what happens is whenever liquid water molecules, which are moving around each other really close together, like my fingertips here, when they freeze into place, they don't freeze into place really touching the way that liquid water molecules do. They spread out a little bit. And so ice expands when it freezes. Ice expands. Water expands when it freezes. So when water gets underneath the pavement on the highway and it gets cold enough to freeze that water underneath, it picks up little pieces of the pavement, breaks them loose, and the cars run over and make potholes. They get into the cracks on the mountainsides in the mountains, freeze, pops the rocks loose. You get a rock slide. Okay? It's why water is less dense. Ice is less dense than water. That's why your ice cubes float and ice rises to the top of the lake, not sink to the bottom of the lake. Okay? It's why the Titanic sunk. All right? Y'all know the story of the Titanic, right?
We should watch that movie.
We're not going to watch that movie.
We can watch the scene.
All right, look, guys. Come on, stay focused here, all right? Okay. We still have a supercritical region up here with water. We still got a triple point down here. Okay? Now, since we know that water on the planet Earth can be in all three phases we're talking about here, solid, liquid, and gas, then we know that the pressure on the planet Earth must be somewhere in this region. Because if we're up here, we couldn't have a true liquid. Okay, we know that our pressure on Earth is somewhere along here. Does that make sense? So this is like one atmosphere fits somewhere in here. Okay? Now, supercritical water or supercritical steam. Let me tell you something that's used for a lot. It's used for especially industrial cleaning applications. Industrial cleaning applications. If you want something to be super clean and devoid of any bacteria, but you don't want to use chemicals like on medical equipment, you'll use supercritical steam or water. Okay? If you want to clean out those tanker trucks, so periodically those tanker trucks, they get gunk inside there because of constituents of the gasoline that settle on the sides and dust and stuff get caught up in there. And you got to clean them off, and it's very hard to clean off. They won't clean off with regular soap and water, so you use supercritical steam. Okay. Supercritical CO2 is often used to remove, and it is used primarily to remove the caffeine from coffee and tea. So if you drink decaffeinated coffee or decaffeinated tea, then somebody used supercritical CO2 for that purpose. Okay?